So if you haven't seen Brave, it's a movie I do highly recommend. And in this clip, Merida, the redhead, has both what we would call accuracy and precision. So today in this video, I'm going to talk to you about what accuracy and precision mean and how they are different, and also show you how you can actually calculate accuracy and precision values so that you can evaluate the quality and the reliability of the data that you collect from an experiment. So let's start with some definitions. Definitions of accuracy. So accuracy is how close you are to your target value. This can also sometimes be called the theoretical value or the known value. You can check it against these values, or you can use positive or negative controls, which we'll talk a little bit more about next semester. This semester, we're mostly going to be able to check our results against a theoretical value. And what a theoretical value is it's basically the right answer. And we know it's the right answer because other scientists have figured out the answer before. So a lot of the experiments we'll do in this class are experiments where we're kind of confirming what has already been studied, for example, density or the temperature of a boiling point or something like that. Here's a visual example. So accuracy in this case, you can see is your accuracy, you're close to that target, you're close to the middle of the bullseye. Precision, on the other hand, is how close your measurements are to each other. So this is more about you and when you're collecting data, or maybe the equipment you're using, and how close those data points are to each other, how consistent you are in your measurements, that kind of thing. So you check this, you have to do multiple trials, but if you're collecting any sort of numerical data, you can always get a precision result. In some of the experiments, we don't have a great way of measuring accuracy if we don't have a known value or if we don't have good controls, but we can always get precision when we're making measurements. And here's an example of precision. So this isn't necessarily on target, but you can see the grouping of those points are close to each other. So those are our definitions. Now, what would this look like in an experiment? So I'm going to show you some sample data from an experiment and talk a little bit about the calculations you can do. So this is an experiment where a tool, these 4 different tools, the P200, the P1000, those are micropipettes, a regular serological pipette and a transfer pipette were all used to try to get 0.2 milliliters or 200 microliters of water. Because water has a very special density of pretty much exactly 1, that also means that 0.2 milliliters is the same as 0.2 grams. So that's our target or our theoretical weight. And basically what the scholar does in this experiment is they use the tool, they use proper technique to measure 0.2 milliliters or 200 microliters, and then you weigh it to see if you actually got 0.2 milliliters. So this is the data from that experiment. So this was done 5 times for 5 different trials, and what we're going to do is these 4 calculations. I'm going to show you how to do these 4 calculations. Over here on the side, I kind of have a guide on how to do these calculations in capital letters. So the cool thing that we're going to learn about Sheets this year is Sheets actually will do math for you, and it will make your life so much easier. This is actually, no matter what career field you end up with in your life, being able to build spreadsheets, being able to use spreadsheets to calculate averages or different other things is going to be invaluable. It was obviously when I was working as a scientist, it was hugely valuable skill, but even if you're working as like a manager of an ice cream store, or if you, in teaching, we use a ton of spreadsheets in order to track scholar data and things like that. So this, across the board, is the most important skill you can take away from this class, is being able to build spreadsheets and being able to use them to make your job easier. Because doing all these calculations by hand would be a real pain in the butt. So yeah, the calculations, how to do them is over here, and I'm going to show you how to make your spreadsheet do them for you. So let's start with average. Average should not be anything new. You take your trials, you add them all up, you divide it by the number of trials. So when we do calculations in Sheets, or this works for Microsoft Excel as well, I prefer Sheets just because I like the Google stuff, you start with an equal sign, and by using the equal sign, that tells the sheet that you want to do math, or you want to make it do math. And you can just straight up type in numbers like a calculator, or it has built-in formulas to do calculations for you. So, for example, if I'm doing average, I can literally just type the word average, and then it pops up with this little thing that helps me figure that out. So I want to find the average of my 5 trials for the P200s, so I'm just going to highlight those cells. Every box in a spreadsheet is called a cell, and that gives me the correct value. If I want to do range, then here's what I want to do. So the range is, if you aren't familiar, it's the difference between your biggest trial and your smallest trial. So this one doesn't actually surprisingly have a good formula for that. You have to kind of do this one by hand, but it's pretty easy. So again, equal sign, let it know we're doing math. And if I look in these 5 trials, the biggest number is 0.202. The smallest number is 0.198, and so that's all I have to do for range. Next, I want my RSD. So this is what's called a relative standard deviation. And when I do this, what I want to do is, again, equal sign. Now this one's tricky, so if you come over here, you'll see that I kind of laid out the calculation for you, but basically you want to do the standard deviation, which is a calculation you would learn about in math. It's a pain in the butt to do, and once you learn about it, nobody ever actually uses it because Excel or Google Sheets can just do it for you because it is super complicated. So this just makes it easy. You literally just type in STDEV, and then same thing, we're going to go back and we're going to select our trials. Okay. And then what we want to do is we want to divide that standard deviation by the average. So this helps us normalize our results, and RSD is expressed as a percentage. So then what we want to do to turn that number into a percent, we just do times 100. So what this calculation is saying is what percentage of our result is the standard deviation. And what we want it to be is less than 2%. Our percent error, this is our last calculation. So our percent error, again, equal sign. What this is this now compares our average value that we got to the theoretical value, which is up here. So what we want to do is we want to take the absolute value, absolute value, by typing ABS, and then we want to take the absolute value of our average, so I'm just going to select the box where we calculated our average, subtract our theoretical, which in this case is 0.2, depends on your experiment, that will change what your theoretical is. And then we want to then divide this again by that same theoretical 0.2. And again, this is a percentage, so we times 100. And that is our percent error. Now, here is where the magic happens. So this is why Sheets can make your life easier. Those calculations, a little tricky to set up, but once you get them set up, you don't have to do this for all your different tools. So what I can do is I can select these, tap on that, and use autofill, and that will do the same calculation, but for my other things. Oh, that's not going to work for this though, because we have to go and do that one manually. So we'll come back to range, but this one, autofill, this one, autofill, and it's done those same exact calculations, but for all of these other things. Now, the range, we do have to do the range manually because they all have different. So let's see, for this one, our biggest number is 0.205. Our smallest number is 0.199. Okay, for this one, our biggest number is 0.215. Our smallest number is 0.191. And then lastly, our biggest number looks like 0.303. And our smallest number is 0.15. Okay, so now we have our data. First things first, let's clean up our data table. Couple things. So we kind of talked about this before, but decimal places is really important. What we want to do is we want to make sure that our decimal places of our calculations match what we have for our results. So what I am going to do is I'm going to change the number of decimal places. I'm going to select all of my numerical data, and then I'm going to go to, not the plus, the little A in the corner, and you want to go to cell. The very bottom of cell, it has decimal places, and you can change the number. We want to set all of those to 3. Okay. And then, just for visual niceness, I'm going to center everything. Okay, so now that we have all this data, what do we do with it? What we want to look at is our guidelines. So these are in the industry called specifications, and it's basically saying which calculation it cannot exceed this number in order to be considered reliable. So let's start with our range. The range is tricky. It shouldn't be more than 1% of your average. So what does that mean? Well, in order to really figure that out, you would have to do another calculation. So we would have to know if this 0.004 is more than 1% of 0.201. 0.006 is more than 1% of 0.202. 0.024 is more than 1% of 0.209, or if 0.153 is more than 1% of 0.228. If you're really quick at this, you could do it in your head. You can whip out your phone and just calculate that. Or the better calculation to use is RSD. So what I would recommend is stick with RSD. It's more of an industry standard anyways. And then this one, let's just not use that. So RSD should be no more than 2%. So this is usually an industry standard. You don't want your RSD to be more than 2%. And what RSD means is that means how far your data points are from each other. So you can tell that just by looking at the data, or you can use this RSD. And what we can see here is this one, that's good. It's less than 2%. This one, that's good. It's less than 2%. This one, not so good. That is 5%. And then this one, also not great. That's 25%. That's a massive precision. And you can tell that by looking at this data, because you've got huge range, huge differences between your data points. As far as the percent error goes, we want to keep that below 5%. So if we take a look here, these three are all less than 5%, so they're good. This one is not. That one is not good. So if we look at these results, we can tell which tools were the most accurate and precise and which ones weren't. So for this P200 pipette, is it accurate, precise, both, or neither? For the P1000 pipette, is it accurate, precise, both, or neither? For the 1 milliliter pipette, accurate, precise, both, or neither? And then finally, the transfer pipette, accurate, precise, both, or neither. Okay, now looking at all of these things, which of these 4 tools would be best to use if we were trying to measure that small volume of 200 microliters? Cool, so hopefully this is helpful to you. We will be doing a lot with spreadsheets. We'll be doing a lot with error this year. So do learn this, come back to this video if you need to, and good luck.